Welcome to Linear Algebra, Chapter 4. Now we're going to look at linear mappings and matrices associated with linear mappings. Now, we actually have already looked at this first section of Chapter 4 in previous lessons, but we're going to review the first section of Chapter 4 and then mostly cover 4.2 as well. But first look here at section 4.1, the linear map associated with a matrix. Whenever we have an M by N matrix over scalar field K, we can always associate with the matrix A the mapping that we call L sub A, going from Kn into Km, by letting L sub A of x equal A times x for all vectors x in Kn. We know that L sub A is a linear mapping, since if you let x and y be two vectors in Kn, let C be a scalar, L sub A of x plus y is A times x plus y, which distributes to ax plus ay, and similarly, L sub A of cx is acx, and the scalar factors out, c times a of x, or a times x. And so we see that anytime we have a matrix A, we automatically have the linear mapping L sub A that's associated with the given matrix A. All right, so next we have theorem 1.1, which says the following. If A and B are M by N matrices, and if L sub A is equal to L sub B, then it must be the case that A equals B. And so this is a uniqueness theorem. So it tells us that if you have two matrices, A and B, with the same linear mappings, then it must have been the case to start with that A and B were the same matrix. In other words, it's unique. There's not two of them. And so let's look at the proof of this result. Okay. Now, what does it mean for L sub A to equal L sub B? Well, it means that A times x equals B times x. Now, let's look at how these are multiplied. The matrix A times the vector x, or the matrix B times the vector x. This means that you're taking the dot product of the ith row of A with x and the dot product of the ith row of B with the vector x for all I running from 1 to m. And then if you subtract the right side to the left side, you have A sub I minus B sub I dot product x is 0 for all I. Hence, that means that A sub I minus B sub I is 0, the 0 vector. Hence, A sub I equals B sub I. Well, if the ith row of A is equal to the ith row of B for all I, that means that A equals B. Simple as that. And so that little uniqueness theorem is immediately established. Okay? And so that's all there is to section 4.1. So now let us proceed to section 4.2. Now, section 4.2 is the converse problem. Here, we're given a linear mapping and asked to find the matrix associated with the linear mapping. So it's the reverse problem. 4.1, you were given the matrix, find the linear mapping. Now you're going to be given the linear mapping and you want to find the matrix. So let's start first with a special case before we look at the general case. Suppose that L is a linear mapping going from Kn into K. Then we contend that there exists a unique vector A in Kn so that L equals L sub A. That is, for all x in Kn, we have L of x equal A dot x. And again, that is a dot product. Proof. Let E1, E2 through E sub n be the unit vectors in Kn. And remember, those unit vectors in Kn form what's called the standard basis for Kn. So if x is a vector in Kn, x1, x2 through xn, then it can be written as x1 e1 plus x2 e2 plus dot 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 plus xn en. So now let's operate on that equation with L. So L of x equals L of the linear combination of the xi, ei's. But since L is linear, we can factor out the xi's so that we have x1 times L of e1 plus x2 times L of e2 plus dot 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 plus x sub n L of en. So if we let the vector A be the vector whose components are, let's say, a1, a2 through an, where a sub I is simply L of e sub I. Okay? Then we see that L of x equals x1 a1 plus x2 a2 plus dot 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 plus x sub n a sub n. In other words, it's equal to x dot product a, or a dot product with x. And so for this special case, we see that the vector a that we need to represent the linear mapping is the vector whose components are L of v1, comma, L of v2, comma, dot dot dot, comma, L of en. We say that this vector A represents this linear map relative to the standard basis script E, E1 through En. So it's easy to find this vector A. It's just the vector whose coordinates are the L of EI's from E1 to En. All right? Now, we want to look at the general case, which is addressed in Theorem 2.1. All right, so let's look at Theorem 2.1. What does it say? We're now going to generalize that special case to the arbitrary case, the arbitrary linear mapping going from Kn to Km. So let L be a linear mapping that goes from Kn into Km. Then we contend that there exists a unique matrix A so that L equals L sub A. Oh, I failed to mention in the special case that the uniqueness part comes from the Theorem 1.1 from section 4.1. Okay, so now there exists a unique matrix A so that L is L sub A. All right, so let's start the proof. Let capital E superscript 1 through capital E superscript n represent, or the symbols be the unit column vectors in Kn, and let lowercase e superscript 1 through lowercase e superscript m be the unit column vectors in Km. So since we have rows and columns, we have to have different notations for the unit vectors in Kn and the unit vectors in Km. All right, now let x be a vector in Kn, all right? So we know that it can be written as the linear combination of the capital E sub 1 through n. And so you have x is x1 e1 plus dot 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 plus xn e superscript n. And if you wrote it as a column, that turns out as, x1 down through xn. All right, then let's let L of x operate on that equation by L, where L is linear. So L of x is x1, le1, dot, 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 all the way through xn, len. But now we can write each of those images that are in Km, Lej, in terms of the unit vectors in Km, lowercase e1 through lowercase em. So there exist scalars in K, a sub ij, with le1 equals a11 lil e1 plus dot 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 plus a sub m1 lil em. So writing that as a column, what is it? a11 all the way down to a sub m1 dot 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 all the way down to L of en equals a1n lil e1 plus dot 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 all the way to plus a sub mn lil em, written as a column, that is a1n down to amn. So you see now we have found actually an M by N matrix A. So here's the matrix A. The matrix A we're needing is A equals the matrix whose columns can be found by taking, like, the first column is L capital E1, the second column L capital E2, evaluated there, dot 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 through L of En. So that's how each column of the matrix is found. Then L of x equals AX, which is L sub A. And so this is called finding the matrix A that represents the linear mapping L with respect to or relative to the standard basis for Kn, the standard unit vectors, E1 through En. Okay, and that's on my next page, actually. We call A the matrix associated with L relative to the standard basis script E, E1 through En. And again, the matrix A is unique by Theorem 1.1 from section 4.1. All right, so let's look at some examples. Okay. All right, I tried to make example 1 and 2 look more easy to understand. Let example 1 be the matrix, the linear mapping F, R3 and R2 be the projection map, where we're knocking off the third coordinate. F of x1, x2, x3 is just the ordered pair, x1, x2. Then the matrix A associated with F is A equals, and the first column is F evaluated at E1, which is 1, 0, 0. And then the second column is F of 0, 1, 0. Third column, F of 0, 0, 1. E1, E2, E3. And since we're knocking off the third coordinate, that's simply the columns are 1, 0, 0, 1, 0, 0. Okay, so that's simple to see, hopefully. Example 2 is another simple example. Suppose I sub n is the identity map going from Rn to Rm. Excuse me, Rn to Rn is square. Then the matrix A associated with I is simply the matrix A, whose columns are the identity matrix evaluated at E sub I, E sub 2, E sub 1 through E sub n. So what's that? Well, it's just E1, E2, En. It's just the identity matrix. So the matrix associated with the identity map is the identity matrix. And I didn't write this one down, but if you look at the zero map, then the matrix associated with the zero map would be the what? The zero matrix. So that's simple to see. Now, example 3. Okay. Example 3, I rewrote it a little differently to the book. Let L be the linear mapping defined in the following way, going from R4 into R2. All right. Let it be defined by the following mapping. L of x1, x2, x3, x4 equals 2x1 plus 3x2 minus 5x3 plus x4, comma, x1 minus x2 plus 4x3 plus 7x4. Then the matrix A associated with L is the matrix whose columns are L evaluated at E1, L evaluated at E2, evaluated at E3, and then L of E4. In other words, the first row is simply the coefficients of the first component, 2, 3, negative 5, 1, and the second row of A are simply the coefficients of the second component, namely 1, negative 1, 4, 7. So that's very simple to see, hopefully. Okay, now finally, let's look at another example, example 4, which is rotations in R2. Rotations in R2. We call a linear mapping a rotation, okay, if its associated matrix can be written in the following form. R of theta equals this 2 by 2 matrix, cosine theta, negative sine theta, cosine theta, okay? And then the matrix is actually what? L of E1, L of E2. Looking at the unit circle, good old trigonometry. So E1 is 1, 0, and E2 is 0, 1. And suppose that our linear map L rotates E1 to L of E1 through the angle theta, and that it rotates E2 to the point L of E2 on the unit circle through the same angle theta. Okay, so we see that L of E1 is cosine theta E1 plus sine theta E2, and then L of E2 is negative sine theta E1 plus cosine theta E2. For example, if we wanted to rotate through an angle of pi over 2, or 90 degrees, then R of pi halves would be cosine pi halves, negative sine pi halves, sine pi halves, cosine pi halves, which is simply the 2 by 2 matrix, 0, negative 1, 1, 0. So that would rotate points along the unit circle through the angle pi over 2. All right, so that is example 4. Okay. Next, we want to observe that the mapping L sub A follows the following format, namely, if A and B are two matrices, then L sub A plus B equals L sub A plus L sub B. And if C is a scalar, L sub CA equals C times L sub A. Well, that's very simple and easy to see. By definition, L sub A plus B of X would be what? A plus B times X. But it distributes AX plus BX, so that's L sub A plus L sub B. And similarly, L sub CA of X is CA times X, which is C times AX, which is C times L sub A. So that's easy to see, okay? And then look at composition mappings. If F is a linear map from Kn into Km, and G is a linear map going from Km into Ks, and suppose that A is the matrix representing F, and B is the matrix representing G, then it turns out that B times A represents the composition mapping G composed with F. So here's the proof of this result. G composed with F of X is G of F of X, or G of AX, which is B times AX. Rearrange the parentheses, you have BA times X. So the matrix associated with G composed with F is the matrix B times A. So it's in the reverse order because remember that B represents G and A represents F. Now look at theorem 2.2. What does it say? Theorem 2.2. Let A be a square matrix, n by n square matrix, then A is invertible, has an inverse, if and only if the columns of A are linearly independent. And you already knew that from entry-level linear algebra. And what's the other thing we know? If the columns are linearly independent, then the trivial solution is the only solution to the homogeneous linear system, AX equal the zero vector. Now, I didn't write out the proof. It's on page 86. You can look at it. But our homework number 8 is on page 87, exercises 6 and 8. Number 6 says, suppose that F is the linear mapping from Rn to Rn, and it has an inverse. It's invertible. Show that if A is the matrix associated with F, then A inverse is the matrix associated with the inverse of F. And then number 8, if C is a scalar and L is the linear map from Rn to Rn, so that L of X is Cx, what is the matrix associated with the linear map? Don't overcomplicate in neither one of those problems. They're not that hard. So work on those for homework 8, and that's all for our video lecture for this section.